All right, our next presentation is by Brad Clark, who is the Vice President of Software Metrics Incorporated. He specializes in software measurement and cost estimation. He currently supports Cheryl Jones at the Army Futures Command. Brad is also our first president for the Bain Center for Systems and Software Engineering. Thank you, Brad, and over to you. Can't hear you yet.
Hello, everybody.
There we go.
It's good to be back again. And one more presentation from me, and then you're done with me. So that'll be good. And this presentation basically is a mini tutorial on general error regression. It's a method. It really appeals to the probably 5 to 7 people in the audience that do data analysis and try to generate trend lines through data to generate cost estimating relationships. In the past, when I've done this, I've used a statistical method called ordinary least squares regression, or often we would do log transforms of the data, so it's called log, ordinary least squares regression. This is a different approach, and it addresses one of the problems that you get when you do a log OLS type regression, which we'll talk about. And then I'm going to try to get through this pretty quick because I have a demo using an Excel spreadsheet that I want to take you through. And I think when you see the demo and how it works, and you'll start understanding, and then you can get this presentation and the demo. Anandi and Julie have them both. And you can, if you're interested, go through it again for yourself. So, and the video too, if you want to hear me walk you through it. All right, so there was an observation made back in '94 that when you have data, depending upon the scatter of the data and its relationships between a dependent and independent variable, you have some on the left. We have the additive error type there, where the error of a trend line going through the data is pretty constant. So you can use an additive model on this data because the error doesn't change over the size of the independent variable. On the right, we have data that kind of increases in error as the independent variable increases. So away from the trend line. So the error gets larger as we get higher in the x-axis values. And in that kind of data, you'd want to model that using a multiplicative model because you have a multiplicative error. And we'll go into this in a bit. In fact, the goal of both the ordinary least squares regression and this technique is to minimize the error. There's another parameter that we want to minimize as well, which we'll get into, but that's the intent of both, is to make a trend line that goes through the data and has the least amount of what we call squared error possible. The general error regression method, or GERM sometimes, is considered to be a better method of regression analysis. It's been in the literature for last 20 years, has become fairly widely feasible today with the computing environment that we all have. You can use Excel and Solver in Excel to do this analysis. The general error regression separates the question of whether estimation error should be additive or multiplicative from the question of whether the shape of the CER should be linear or nonlinear. You give the cost analyst the freedom to model any CER functional form. And there's a special form here where you have Y, which in our case is usually effort or cost, equals A, that's a constant that is derived through the regression, plus B, another coefficient, or another coefficient actually derived from the regression, times X. X is our independent variable that varies, and then raised to the C power, which is another coefficient we derive. So general error regression breaks the bonds of OLS regression but it requires the analyst to be able to minimize an error function using numerical optimization techniques, and it's possibly doing this using Excel solver function. So typical forms of cost estimating relationships, CERs, Y is typically your cost or dependent variable. X is a parameter or independent variable that varies. A, B, and C are coefficients that are derived from analyzing the historical data. So in the first CER, we have Y equals AX. So it's just A, which is some number, some coefficient, times X, the independent variable. You can have Y equals A plus BX. This is a common form that you see in algebra with the intercept and the slope, the intercept being A and B being the slope. You have nonlinear CERs where you have exponents in the equation. So A times X to the C, A times B to the X, and A times or A plus B X to the C. Now the Kokomo model, I've worked a lot on the Kokomo model and calibrating it. It is more of the A times X to the C, although we have some other terms that we also multiply in this equation. Here, this last form here, though, this A plus BX to the C is a versatile form because in your analysis, if you find out that C equals 1, then it just becomes the simple A plus BX. If you find out that A is 0, then it becomes the A times BX. So using this form is a very versatile way to do analysis because terms can drop out depending upon the values of A and C. So from now on, by convention, we have Y hat, and Y hat is basically one of these model forms that we're going to try to derive the exponents, the coefficients for the different parts of the model. So A, B, and C for this this bottommost form. In the additive model, which we talked about first, where the error is fairly constant, the error is basically you have the actual value of Y, which could be effort or cost. You have the estimated value of Y plus some error term, which is expressed by the distance of the estimate from the actual in the plot. And you can determine the error by just doing the simple math of solving for the error, and you get the actual minus the estimate. We desire to choose the Y hats, the F of X's, the coefficient, so the sum of the squared error is as small as possible. So pretty standard here. Same thing's done in ordinary least squares regression. And what you do is you sum up the square of the errors. The square term here makes anything that's negative positive. So it's a way to have positive values, and you want to minimize then the sum of all these errors. So if you have 100 data points, you're going to have 100 yi minus y hat I squared, and then you're going to sum all those terms up. All right, so far pretty simple, straightforward, same as OLS, what it's trying to do. So we have this model form where you have Y hat is estimated by A plus B to the X raised to the C. We're trying to solve for A, B, and C. What we want to do is reduce the error. Again, it's just Y minus Y hat for the coefficients that we derive for A, B, and C. And the error should be as close to 0 as possible. So if it's at 0, you've got a perfect fit. So same thing said here, ABC, choose it so that the sum of the errors is a small, and then we can use solver to do that. In today's demo, I have the additive model in there and how it works, but we're just going to focus on the multiplicative model. In the multiplicative error model, here the error is increasing as the X value, or in this case, its weight, increases. So now we have Y equals Y hat times the error. And the error is the ratio of the actual to the estimate. So it's yi. So if you do the division here, you get the error as yi divided by y hat, which is the actual divided by the estimate. You choose your y's, the coefficients in your function or your specification, so that the sum of the square percentage errors are as small as possible. So here we have the error -1 squared. We transform that into yi over y hat, which is what we have up here. Hopefully you can see my little cursor moving around. -1, well, 1 is y hat I over y hat I squared. Then we can simplify that by its the simplified form is the actual yi minus the estimate y hat I divided by the estimate y hat I squared. This is different than what we have seen and what I've done actually in my research. We usually subtract, we subtract the estimate from the actual divided by the actual. This is different. This is a percentage error with the estimate being kind of the base. But so this is a different kind of thing. And when I first saw this, I'm like, what's going on here? I've never done it this way. When you see things like MMRE, mean magnitude relative error is actual minus estimated, or yi minus y hat I over yi, not y hat I. So a different way of measuring error. And the way of doing this is known as minimum percent error. And this is the error term that we analyze with our analysis tool in Excel. Again, here's your model form. I've heard it called the triad. You have A, B, and C are coefficients. X is your independent variable. You want to reduce the error, so it's y equals y hat times the error. The error is equal to y over y hat. You want the error to be as close to 1 as possible, not 0. 0 in the additive case, 1 in the multiplicative case. And then you choose A, B, and C so that you've got the smallest minimum percentage error, MPE, possible. And again, the demo will show us using Excel to solve this this problem. Now, another consideration that we don't do in ordinary least squares regression, but this is what drove the cost community to fitting data using this type of method. The minimum percentage error procedure tends to produce estimates that are biased upward. We'll see this in an example. The net percentage bias is the algebraic sum, including positives, negatives of all the percentage errors. These are the percentage errors here, the yi minus y hat over y hat. All percentage errors made in estimating points in the set of observations. So it's the algebraic sum, and what you do is you take the average of all of those fits. So if you have 100 data points, you're going to have 100 of these errors, multiple percentage errors. You're going to add all those up and divide, and then divide by 100, because n will be 100 in that case. And that gives you net percentage bias. So the word bias and this idea of bias really intrigued me. Wow, never heard of the term, didn't, wanted to see how it worked. So what happens is when you're minimizing the sum of squared percentage errors, and the same happens when you minimize the sum of the squared errors in the additive models, it does not also minimize bias. You can have bias where the model estimates, overestimates or underestimates the trend line. So bias gives you kind of an idea of the accuracy of the trend line. Minimize the error to as close to 0 as possible gives you a precision. So is a biased CER a bad thing? So when we use OLS, it turns out that we have bias CERs. They create bias CERs. And depends on whether you'd rather have a minimum standard error, okay, low error, or with a bias using OLS, or an unbiased CER. So you might have a larger error, a slightly larger standard error, but with no bias. And it really boils down to a question of precision, and precision here is defined as the minimum error. It's either the standard error for additive models, standard percent error for the multiplicative models, over accuracy, which is you might a lower bias or no bias, but you have a larger standard error. So there's a trade-off. You can go to zero bias, but your standard error will probably be greater than if you went the precision route, just reduced on the error, and you're going to have a bias. Generally, cost estimators prefer accuracy, which is the no bias option, over the precision, which is the lowest possible error. So we have this minimum percent error based CER can be modified to eliminate the bias. And we use what's called the zero bias minimum percent error method, or ZIMPI. And in ZIMPI, we minimize the error of the squared errors with the added constraint that the bias will be equal to zero. So while we're doing while the tool is working to find the best coefficients that reduce the error as close to zero as possible, while also making sure there is no bias, the bias is zero. All right, so we minimize the squared errors, constrained by the average of the sum of the squared errors is equal to zero. You'll see these equations again in our little demo, so don't worry about trying to remember all this. So the same as minimum percent error, but constrained by holding the net percentage bias to zero. We have a constrained optimization problem where we minimize the sum of squared errors. In adding constraints, it reduces the trade space, leading to a higher standard error. ZIMPI leads to CERs with zero net bias, percentage bias, but increases standard error. And we're choosing, in this case, accuracy over precision. And our demo will show this. So another fallout of using this general error regression method is that we can no longer have access to the statistics that you get when you use the ordinary least squares, OLS method. So we don't have the coefficient determination, the R squared, T statistics, F statistics, ANOVA analysis, and all the other things you get when you do a regression analysis using OLS. So what we have to do is come up with some other model goodness of measure statistics. And one is the standard error of the estimate, often seen as SE or SEE. The bias, how well does the CER go through the middle of the data? Want this to be as close to zero as possible. And then instead of capital R squared, we use Pearson's correlation squared, so small r squared between actuals and estimates. So this is basically just a correlation. The coefficient determination measures the model fit to the data, but Pearson's correlation measures the correlation between actuals and estimates. And we want this to be as close to 1 as possible. So we're changing the goalposts here, looking at things differently. But in our example, if I have time, we're going to compare an OLS analysis and a ZIMPI analysis of the same model on the data set, and we're going to see how those numbers are different. The standard error estimate is a square root of the mean of all errors or percentage errors made in estimating observations in the data set. A one standard error number can be used to bound the actual cost with an interval surrounding the estimate. So it's similar to 1 sigma when you're taking averages. The additive error model basically sums up all the errors. So it's just the actual minus the estimate squared in an additive model divided by the number of observations n minus the number of parameters in the model k. So it could be 1, 2, or 3 parameters. It's 3 for that triad model that we saw earlier. We'll see again. In the multiplicative case, we have now the sum of all of the percentage errors, and we already have gone through how we derive this estimate minus actual divided by the estimate. All those are squared, again divided by the number of observations minus the number of coefficients in the CER that we're trying to derive coefficients for. How do we calculate bias? So bias for additive models is the algebraic sum, both positive, negative. It's not squared or absolute valued. Positive, negative, all errors made in estimating observation data set. So it's just basically the sum of all the errors, and you divide it by the number of observations. There's your average. The net percentage bias for multiplicative error CERs is the algebraic sum, positive, negative, all the errors made in the estimating observation set. So here we have the percent error here term, and we have the 1 over n, which takes the average of that. What you want to do is constrain net bias to 0 while the tool is trying to figure out the best coefficients to drive the error as low as possible. So this is how we calculate bias. This is how we calculate error. These are 2 important calculations that we have to set up in Excel so that the solver can work with the results of the error and the bias. Pearson's correlation squared. Basically, it just measures the extent of correlation between estimates and actuals. The coefficient determination, it's a kind of an analog for that. But it's not the same thing. And it provides insight into how well the estimates match the actuals to which they correspond. The shape of the data does not matter for Pearson's correlation. And then this is Pearson's correlation equation. We don't really have to worry about that because there's a function in Excel called correlation. You give it the actual and the estimated values, you square that term, and that creates our small r squared. You'll see that statistic in our demo as we run through some analyses. The first thing you do to use germ is you plot the data. You choose the functional form that models the logical impact of the independent variables, stuff on the y-axis. On the dependent variable, the stuff on the y-axis, the x-axis has the independent. You can have y equals a plus bx. There's an additive type model. Y equals a times x to the c. That's a multiplicative model. And the y equals a plus b times c to the x to the c. That's also a multiplicative model. And that's the model we're going to be looking at, because if c becomes 1, it drops out. If a becomes 0, it drops out. When we start doing the analysis to determine what the value of a, b, and c are going to be. Choose either additive or multiplicative error models. Additive, you want the error of the estimate to be expressed in a uniform amount across the entire cost range. Multiplicative, if you want the error of the estimate to be expressed as a uniform percentage of error of the entire cost range. Selecting starting values for A, B, and C that minimize the error. So we're going to use the value 1. You might have information where maybe 1 is not the best value to start with, but you put in 1. You want to constrain the bias to 0, and then you want to run the tool and solver that solves for A, B, and C and the net bias. And I think most of this is going to come alive when we do the demonstration. I think you'll see kind of how this mechanics work. Now we're going to look at 3 things. We're going to look at the basically your multiplicative percentage error, your basic model that does have a bias. We're going to see that bias, how it's done. Then we're going to run Zempi and eliminate that bias. And then we're going to compare a model using the log OLS regression and Zimpy and see the different results, see how they differ. This is where I was really motivated in learning this technique is, all right, so people say, you cost guys, you say all this good stuff. So I really want to find out what we changed the goalposts as far as measuring how good things are. Okay, so if I have the same data and I can run log transform data using ordinary least squares regression, and I can run Zimpy, what's the difference? Is it better? Really? I mean, let's see. So let's go explore that right now. Let's see. I'm going to change. Here we go. All right. All right. This is a spreadsheet that comes with this presentation. There's a bunch of tabs down here. There's an additive model set up, the additive model executed. I said we're not going to cover that because I want to really move on to the other things. We're going to start with a multiplicative model setup. I'm hoping all of you can see this. If I haven't mentioned this, it's on the presentation. It's in the spreadsheet. This whole presentation is based on a person named Tim Anderson. He has a course module in engineering economics and cost estimation. It's a Naval Postgraduate School course, and this is taken from the fall of 2020. Did a great job at explaining this, and I've seen this technique used other places and could never really keep up with the different things that they were doing to remember it all. But he did a great job at doing this, so I kind of follow his example. I've added some things in here that I thought might help us understand what's going on. All right, so here's our CER up here. Y hat equals A plus B times X raised to the C power. We're going to derive the coefficients for A, B, and C. They are down here. Here are the coefficients, and initially we're going to pretend, we're going to say we don't know what these are. We're just going to set them to 1. We have to have data, so we have cost and weight here. So cost is what we want to predict. Weight is our independent variable. Over here we have the chart that you've seen before, and we can see that as weight on the x-axis increases, we see that the space of the data points diverges. And I see this a lot in the Kokomo cost data where you have size and effort. And as size gets larger and larger, effort starts diverging from a trend line. So this is perfect data for a multiplicative type model because as the dependent variable increases, the error amount of error increases as well. So we have our cost Y, we have our weight X. The first thing that we do before doing any, before running any tools is we create the estimate. Now, how do we do the estimate? Well, we do it because down here, we've made an assumption of values, 1, 1, and 1. So we use these values in creating our estimate. Even though they're wrong, we're going to get solver to change those values. But right now, we set it up where we have 1 plus 1 times x to the 1 for every one of these. And you can see that the difference between 2.8, which is x, and 3.8 is 1, because 1 plus 1 times x to the 1 is just 1 more than x. So you can see that this 3.8, here's 3.0, it's 4.0, 3.6 is 4.6, and so on and so forth. All right, now we have our initial estimate based on our best guess parameters. Next thing we want to do is we want to create our error term. First thing we have to do is create the difference between the actual y and y hat, or f of x. So y minus y hat, or y minus f of x. Here's our error. So that is y, 88 minus 3.8, you get 84.4, and so on for data points. Next, we want to create our percent error. So that's where we have the error divided by, so it's actual minus estimated, divided by the estimate. That was back in the presentation. And we get our results here by doing that. When you get the spreadsheet, you can click in these cells. You can just basically see how these are all done with variables. And then we want to take this error and we want to square it. So our percent error, PE, is squared, which are these values here. At the bottom, what we do is we want to do the sum of the squared percent errors. So we basically sum all these up because they're already squared, and we get this large value. Now what we want to do is we want to have solver change these coefficients. And when it does that, it'll change these values here, which are all based on these coefficients, which in turn will propagate through our error model and change all of the squared percent errors to get a new error. And we want solver to change these so that this becomes low as possible, as close to zero as possible. So that's how solver is going to work. All it's doing is looking at is changing these to minimize this. All right, so that's what we're going to do. Here's the model that's already been run, so I'm going to go ahead and initialize it. All right, so we have ones for A, B, and C, the same as the spreadsheet before. We have a little plot here. Don't pay any attention to that right now. Now let's invoke solver, and in Excel under the data tab. For the Macs, it looks like this. For the PCs, it looks a little bit different. But for our set objective for solver, we set the sum of squared percent errors. And what we want the objective to do is to minimize that. You can do maximize, minimize, or set a value of it. We want to minimize it. And then how can it do that? We tell it which cells that it is allowed to change. It's allowed to change these cells over here. Fantastic. There's a check mark here about make unconstrained variables non-negative. We don't select that. We're going to use the default GRG nonlinear. We're just going to say solve. All right, so solver's off solving. Watch these over here, these values, and they've changed. And solver says, I'm done. Okay, so we've got an initial set of values. We accept that. Now we run solver again. So you're going to run solver, as the note says here, multiple times until the values are stable. They don't change anymore. And it minimizes this number here by changing these values over here. So hopefully you guys are still hanging on here. All right, we're just going to solve again. Watch over here for A, B, and C. It changes again. All right, let's do it one more time. Oh, it's still changing. I was too quick. Okay, 136. All right, now it's done. So it came up with 142 for A, 1.98 for, accept that, 1.98 for B, and 1.44 for C. Great. Will it change again? So we're going to run one more time just to see if it's become stable. So we're running it. Will these change? Nope. Okay, we're done. The values didn't change, so we're at a stable state for solver. Now we want to evaluate these numbers. So the first thing we do is the percent error, standard percent error, which is this equation from the presentation. Remember, we're taking this percent error and we're dividing it by the number of observations minus the number of parameters. In this case, parameters are 3. So it's 0.38. We'd like that to be as close to 0 as possible. We have the Pearson R squared, which is just the correlation between the estimated and actuals. So here are our actuals, and with the new coefficients, here are the estimated. So we do that. In fact, I can just highlight that. There's your function as well. And then we have the bias, which is the average of all of the percent errors. So we take this percent error column here, we take the average of all this, positive, negatives, and we get a minus 12%. So the negative bias is due to the estimate being more than the actual, because we take the actual minus the estimate. Estimates must be more often higher than the actual. So what we have here is a model that overestimates the actuals 12% of the time. All right, so we look over here at this chart, and I have the percentage error here, and I have a trend line based on our model. And what do you think? does this trend line go through the data points exactly? Or is it above or below the trend line? What do you see just by observation?
This is Jim. I think it's a little high.
I agree with you, Jim. I agree. And that's the indication of our bias. So the bias means the estimates are being more than the actual cost, and the trend line, because of the estimates being more than the actual, it's higher. So it's not really through the data, and we want that to go through the daggone data. So now let's go to the Zimpe method and see and fix this. Okay. All right, same problem, right? Same exact setup here. Same model, data. We calculate our estimate based right now on 111. We don't know what the real things are going to be. We're going to figure what that is later. Once we have our estimate, we can compute an error, then our percentage error, and then we can square the percentage error, and then we can get the sum of the percentage errors here. And just like in the last one, last case we just ran, we're going to use solver to minimize this. And we're also going to use solver to work with our bias. So here it says run solver multiple times until the values are stable. So we want our A, B, and C to settle down to some value that doesn't change, and constrain the bias to 0. We want this to be 0. So let's go do that now. All right, let's see. 1, 1, 1. All right, we have right now with our model set at 1, A1, B1, C1 up here. This is our current error. It's huge. We have Pearson R squared 0.46, and our bias is huge too. And this chart's all messed up. So don't worry. Let's not worry about that. Let's jump into using solver to figure out what our A, B, and C is and see what happens here. All right, so the first thing we do is we want to set the objective, which is this cell right here, and this value, which is our sum of squared percentage errors. We want to minimize it. So you pick the minimum button. And then we want it to changing variable cells, and we give it these 3 cells here. If you've got more variables, you're going to have more, for every coefficient, you're going to have a cell. So you could have 10 variables, you're going to have, 11 cells. It just depends. In this case, we have 3. So, we highlight all the cells that are applicable. And then what we want to do is we want to add the constraint that the bias, this number has to be 0. So what we do is we go over here and we hit add. We give it the cell. We tell it's this cell right here. What do we want to do with it? We want to set it to equals. And equal to what? We want it to be equal to 0. So add that constraint. Did it do it? Yeah, it did. Okay. So here's our here's the objective. By changing the variable cells subject to the constraints, we want B30, which is this cell here, equal to 0. Same solving method. Don't change anything. Don't click this box. Now let's go hit solve and look at these cells over here, A, B, C, and see what happens. Changing, boom. Solver says I'm done. Okay. Let's solve again and see if these values change again. So we have the 111. Now we have a different set of initial values. Let's go ahead and solve again. We are all set up. We hit solve. Changing. Still working. Still working. It says it's done. So the values now are 125 for A, 1.66 for B, and 1.44 for C. We have a bias of 0, and we have a standard percent error of 0.41. When we used MPE, it was 0.38. It was lower. So our percent error is raised. And we have 0.46 for our correlation, and that hasn't changed from the MPE runs we did. So now we have 0 bias. So if we look over here at the chart, the blue line now is the ZMPE line, and the red is the MPE line. And we see the red is still kind of high to the data, but the blue line appears, it's kind of hard to see because we got all the stuff going on here, all these lines, but it looks like the blue line actually is going through the data evenly, kind of splitting it, right in half. Yet we've got a little bit higher error. So this again comes to precision or accuracy. Which one do you value most? The two models are here. You can see the coefficient differences, although that's also over here. ZIMPI got 1.25 for A. The MPE was 142. The beta value was 166. MPE was 189. And then the C value is the same. The exponent 1.44. So interesting, how you can have models that with a bias, they actually don't quite go through the data. But I thought, I really want to see how ordinary least squares regression works on this. And fortunately, I've been talking fast enough that we can do that. So I have another tab here, the OLS comparison. Now you cannot, there's no way to transform this model into a form that you can do OLS regression. You can only use this in an iterative nonlinear technique. So I had to basically change models. So we changed it to B times x to the C. This is a kind of a Kokomo thing. And what we do when we use this, when we want to do linear regression with a multiplicative nonlinear model, multiplicative only, nonlinear because of the C, we do a log transform. We transform the Y values, our dependent variables. When we do the transform, B becomes a coefficient we can derive plus, and then C, another coefficient times the log transform of the X values. So here we are back at our data. I have cost and weight. I did a natural log transform on them. So I have the natural log of the cost and a natural log of the weight. And then from here, we can roll forward and do, well, let's stop here. So I have the natural log of these two things. So what I did was I took this data and I ran it through Excel's regression model. So you can get, it'll do regression and up to a certain number of variables for you. So I have as my input range log of Y, my X input range, the independent variable, log of X. I have labels, great. My output's going to be down here, and then I can say okay, and it produces these statistics that we are used to seeing when we do OLS regression. So we have here an R squared of 0.58. We have a standard error of 0.42. The R squared is the capital R squared is coefficient determination. It's a different than a small r. Okay. We have our degrees of freedom and so on, and our sum of squared errors. And then we have our coefficients that were derived, our B and our C for our model here. So the B, you have to take the anti-log of 4.29 and you get 73.1. And for C, you take the anti-log of C times the log of X, it's just X to the C. So you just use that as a straight value in the model. The model looks like this. It's cost times 73.51 times the weight raised to the 0.046 value. Anybody's this is nothing. Everybody knows this that has done analysis this way with multiplicative models, log transforms, and you got to go, transform back and all that kind of stuff. All right, so we get all that. And we look now, what I did was I said, okay, so that's our stat tool here. That's what I've been using for the last 20, 25 years. Great. Well, what about this, these other measures of performance that we use in the general error regression method? So we calculate the value of the estimate here. And when we use this, we basically use this equation, and the B and C are defined down here. So if I click on this, you'll see there's the B, there's a C. It's in this formula. Great. I calculate y hat from our derived coefficients using OLS regression. Great. Then I calculate my error that we do in the general error regression technique. Then my percent error. Great. Then I square my percent error, and then I get my sum of squared errors. And then from this, I can derive my standard percent error, which is 0.5. If you look at the standard error from the regression, it's 0.42. The Pearson R squared is 0.43. Has nothing to do with the R squared. And then the bias, though, is 0.09. And a positive bias, because of the way that the error is calculated, is due to the actual being more than the estimated cost. So if we look at this chart, and here is the regression line, we see that it is slightly low. It doesn't quite bisect the data. The first time I saw this technique, a different presentation, the presenter said, log ordinary least squares regression underestimates consistently the actual data. And I thought about that. And I thought about a meeting I was sitting in with Barry and a bunch of other people who were doing the Kokomo book and things. And a comment was made, yep, it's well known that Kokomo underestimates cost. Well, why is that? Because when we analyze Kokomo, we use this log transform technique. Because the stat tools can handle 23 variables, right? I'm not sure Solver. I'm not sure how many days it would take for Solver to work on 23 coefficients, but we have this underestimation phenomenon for log ordinary least squares regression. Interesting. So let's take this example and drive it over to Zero or Zempi. All right, same data. Reinitialize here. Same thing you saw earlier. We put some values into our B and C, our coefficients for B and C. Calculate a y hat or the estimate. Calculate the error between the estimate and actual. Do the percent error. Then square the percent error to get our sum of squared errors down here. Okay, we got that. That's good. Here's our two things. And then we want to set this bias to 0. So let's run Solver again with the constraint. All right, so it says set objective. Here it is, the sum of squared percent errors. Changing what variables? You can change these two variables, Solver. When it changes these variables, as Solver changes these, it changes the values here, because these values depend upon these two variables, which changes the error and propagates down to the sum of squared errors. Okay, good. And then we want to add a constraint. So we're going to say cell reference, it is the bias. So it's B30. And we want to set that equal to 0. Okay. So here's our constraint. Don't make unconstrained variables non-negative. The GRG non-linear, same thing, hit solve. These are going to start changing, the B and the C. And of course, as they change, you'll notice that the estimates are changing too. All right, Solver says it's done. Okay, let's run it again just to see if these values are stabilized. Values didn't change. So we have the B is 61.4. It was 73.5 using OLS. C is 0.55. It's higher than OLS 0.46. And the bias 0. All right, let's go look at the chart over here. So we have the log OLS here, the red curve. It does look like it's low, underestimating. And we have the Zimpe curve. Basically, this is the prediction line. And it does look like it's more through the center of the data. I find that fascinating. And here are two models. You can compare the coefficients down there. All right, so this is available for you to play with. Let's go back to the presentation. Almost done. I got one more slide. We had fun. At least I enjoy playing with numbers and seeing stuff change. All right, so here are the conclusions. Last slide. What's more important to you, the audience that cares about this stuff? Is precision more important? In other words, a minimum standard error or standard percent error, or is the accuracy more important? You might have a larger error, but a low or no bias in the model. So that's something to ponder. And I personally, I kind of think, well, accuracy seems like okay to me. I mean, I'll probably go with accuracy. Number two, which is the correct multiplicative error model? So in the presentation, we had actual over estimate, which results in the actual minus the estimate divided by the estimate squared. And that's what's used in MPE and Zimpe. And I thought, this doesn't make sense. Why would you do this? You don't care about the estimate, you care about the actuals, which has been basically my upbringing in Kokomo and relative error and mean magnitude relative error and all those terms and PRED and all that stuff. Or is the multiplicative error, is it estimate over actual, which results in the estimate minus the actual divided by the actual? This is kind of what we use for judging our Kokomo accuracy. So I have a hard time with this one. And what I would probably do is go back to that spreadsheet that we just went through, and I would change the way, make another version, change the way that the error is estimated to this, where it's relative to the actual, not relative to the estimate. And then look to see if the results were the same, to see if the trend lines were the same, to see if the lines created by Zimpe looked like it still split the data, or if it just went way off the charts. And then maybe I'd be convinced that, well, it's the first one, not the second one, that we should probably use. And then the third thing is, what is the best way to choose the initial values for A, B, and C? So I put in 1.0, which makes sense if you've got an exponent in your model that you're trying to analyze. If you don't have an exponent, maybe you could start with 0 or some other value. And I haven't gone back and played with putting in 100, 100, 100, 100, the value 100 for all three, and see if it doesn't matter. It'll still figure it out. One of the things I was thinking was the initial values can be set by doing OLS regression, which will get you pretty close. And then you run Zimpe and constrain the bias to 0, and it will just refine those results. Well, that works fine on that multiplicative model, but it does not work fine. You can't use it on the triad model. There's no way to convert that using any transformation process into a form that you can use ordinary least squares regression to suggest the initial values. So for right now, I guess we stick with 111. There might be a better way to do that. I kind of am concerned going through computer science many years ago. There was a concern about local minima versus global minima. And can you fall into the local minima, which means your model's brittle if you don't, if you have other data, the model will perform well because it's not in the same locality as the other data. I don't know. It's more of a theoretical thought. Anyway, those are food for thought. Thank you for hanging on here. These are different additional references. We showed this one earlier. If you look at, Tim Anderson, who's did this tutorial, and I just basically adopted it for this presentation. Stephen Brook is kind of considered the guy that has put this together, and he's got multiple papers in the Journal of Cost Analysis, or might be later, I think they call them the Journal of Cost and Parametrics. There are the references that talk about using these different techniques and why additive multiplicative error matter, and that matters to your model form, and then how you measure error and what you account for. They've done studies, for different things. So there's some more reading if you guys are interested. And if anybody has a question, here's my email. Send me an email. My company email isn't working and I've got to fix it. So yeah, please enjoy. And got any comments, please make them. But otherwise, look forward to you guys getting this, and then getting email probably 5 months from now going, hey Brad, when you do this, did you notice this? Be like, no, let me go do it and see what's going on. But anyway, have fun with this. Thanks a lot. Appreciate your time.
Brad,
Yes, sir.
I want to second Dan's chat message. I think it's a terrific presentation. You went through the theory, and then you showed people how to use the solver in Excel. So I think it's just a terrific presentation.
Thank you. That's my kind of thing is, okay, show me kind of the background and the math things, and I can kind of understand the math things. But once I see it in action, I go, okay, now I can go back to the math thing and I can really understand what those things are doing. So I like teaching this way, where you do, the modeling underneath, and then you get to finally see something live that works. And I tried to the presentations I've had before, like I say, I was hanging on with my fingernails because the guys weren't slowing down. They weren't trying to explain things. And I figured, well, to make this, if people are going to use this, they have to kind of see it and get it and understand it and see the differences and how it all changes. And the solver thing intimidated me for a long time. Finally get over that. Not that hard to use. How you set things up. And now I'm wondering, for the Kokomo model, I wonder if I went back to the 161 data and set that up with the 23 coefficients we need to calibrate that thing. I wonder how that would work out. Just curious. I'm just thinking solver would has to take a long time to do that stuff. I wonder if we, anyway, we'll see. Thank you all very much for listening.
Thank you, Brad. And I agree with Jim. That was really good. Like you, I've sat in other presentations talking about these topics and I could never really follow, but this I feel like I got. So thank you for that.
And now you get the spreadsheet to go play with, so you can, try it out if you want.
Exactly.